Hey grade 11s, here's the things I was going to go through on the Teams recording today, so I figured I'd just do this and post it, and you guys can go through it at your own pace. This is kind of the stuff that we'll be looking at for the next week or so, and a little bit of review of the stuff that we've done kind of this week. So, a couple of things I want to clarify, a couple of things that I find that lots of students maybe not struggle with, but kind of get mixed up, is dissolving. So there's two ways to look at dissolving. I want to talk about making things dissolve more quickly and making things dissolve better. So in other words, if you're trying to get something to dissolve, how can we make it dissolve faster? And how can we make it more soluble? So dissolving more means solubility, and dissolving more quickly just means how fast you get it to dissolve. So if we want to make something dissolve quicker, there's a few ways we can do that. To make things dissolve faster, you can heat them up. So you can usually, with solids especially, if we're talking about solids like we are here, you add some heat and it will dissolve more quickly. The other thing is you can increase the surface area. So things like grinding it up into a powder will increase the surface area of your solid, and it actually exposes more of it, so you'll get more collisions between the solute and the solvent, and it dissolves faster. And then the other thing you can do is you just stir it or agitate it. So if you think about making hot chocolate, if you've ever tried to do it without heating the water first, it doesn't work so well. It doesn't dissolve very quickly. You can get it to dissolve, but it takes a lot of stirring, a lot of time. So stirring it also helps. So heating the water first, stirring it in, and also putting your hot chocolate in as a powder rather than one big chunk. It obviously would dissolve more quickly as a powder as well. So this is kind of the idea behind that. Now, if we want to make something dissolve more, especially in terms of a solid, only one of those three things will actually get more solid to dissolve, and that's actually heat. So if you want to make more solid dissolve, if you want to increase the solubility, you need to add heat. Now, the reason why adding heat to a solid makes it dissolve better is because the solid is being held together by lots of intermolecular forces. We've been talking about those. To break those, you need energy. So the more energy you have, the more solid you can break apart. The other thing is to make a solid dissolve better, sometimes things aren't that soluble in water, so maybe you choose a different solvent. And that brings up our like dissolves like rule. If you use a solvent that's a lot more like the solid that you're trying to dissolve, it will dissolve better. So if you have like a chunk of grease or something like that and you want to dissolve it, well, obviously water's not a good choice. It's not very soluble in water. So you would choose something that's maybe more like that. There's lots of solids that don't dissolve very well just in water. They dissolve better like in vinegar or acids. Some dissolve better in bases, those kinds of things. So you would choose a solvent. So there's really only one true way to make something dissolve better in water, and that's just, to dissolve more in water. That would be adding heat. If it was a gas, you would actually make it colder. Gases dissolve better when they're cold. Dissociation now is something else that is super important for grade 12. So I just want to go through a quick couple dissociation reactions. So magnesium chloride is an ionic compound. It's MgCl2. If we're dissolving a solid particle of that, it's going to dissociate into its ions. So magnesium ions and chloride ions. Now you're going to get two chloride ions. Notice it's a coefficient 2, not a subscript, because you've got two separate ions being made. And these are what we call aqueous, or in solution. Now, I see lots of students forgetting their charges. It's important to include charges because there's a big difference between a magnesium ion and a magnesium metal atom. One could be stable, one is not stable. So that charge makes a huge, huge difference. Now, these ionic compounds, when they're dissolved and dissociated, are electrolytes. Why? Because they have charges and they're solutions that conduct electricity. And you've probably heard about electrolytes in things like Powerade, Gatorade, that kind of thing, and that's all it is. They put some sort of a salt in there that dissociates, creates some ions, and it replaces the ions, the salt that you're losing when you sweat. All right, so that's solution formation. Again, same thing here. We're going to do a couple quick dissociation reactions, and I'll get into the solubility table because that's the main thing that I wanted to talk about today. So AlCl3 is an ionic compound again, so it's going to dissociate into aluminum ions, and aluminum ions are 3+, and you're going to get 3 Cl- ions, and those are aqueous. So there's your dissociation reaction. Now PCl3 is covalent though, so it's not going to dissociate into ions, it stays together as a molecule. It's a non-polar covalent, like it's just a pure covalent molecule. So we're going to just get PCl3 and it's aqueous. Remember, ionic compounds will dissociate, covalent compounds will not. So it just goes into the solution if it's soluble. All right, so that's just a quick review on dissociation and solubility. Now, we have a curve that you will be using, and it should be in the lessons, and it looks something like this. This is called the solubility curve, and it tells us how much of a solute can dissolve in 100 grams of water. Now, 100 grams of water is the same thing as 100 mils of water, because the density of water is 1 gram for 1 mil. So 100 grams is 100 mils. It's the same thing. So we can kind of use that interchangeably. Now, what you're going to notice is most of these lines move upwards, and that's because solids tend to dissolve better when they're warm, again, breaking more bonds. Some aren't affected very much, like if you look at NaCl here. NaCl doesn't dissolve much better the more heat you add, but it does increase a little bit. There are a few that go down. So we're looking at like HCl, NH3, and SO2, and they're dropping because those are gases, and gases dissolve better when they're cold. Because with gases, the bond's already broken. You're actually trying to form bonds. In order to make bonds, you got to take energy out. To break bonds, you got to put energy in. So to break apart solids, we put more heat in, you can actually get more to dissolve. To get gases to bond with stuff, you need to slow them down. You need to take energy out of them. So that's what this chart is kind of showing us, and it gives us basically at any temperature how much we could dissolve in 100 mils. Now we chose 100 mils because it's a small amount, and also 100 is an easy number to work with because we can just factor up multiples of 10 or 20 or 50 or 5 or whatever, but it's easy math to work with that ratio of how many grams per 100. So I'm going to do a few examples of what kinds of questions you might see. So if we are looking at question 2 here, it says use the solubility table to answer the following questions. 100 grams of water saturated with sodium nitrate at 40. If the solution is heated to 70, how much more can be dissolved? So if I go back to my chart, we're talking about sodium nitrate, so that's NaNO3, and we're looking at 40 degrees, and NaNO3 at 40, here's your solubility. That's saturated. Saturated means the solution is full. It's holding the maximum amount. If you were able to get extra to dissolve at that temperature somehow, that means you're supersaturated, you're oversaturated. And if it's below, that means you're unsaturated. There's more room for more to dissolve. So it says the solution is saturated at 40, so it's holding 105 at 40 degrees, and then I'm going to look at 70 degrees, and it's about there, and that's about 135. So if I go back to our question, 100 grams of water are saturated at 40, so at 40 degrees Celsius, we can hold 105 grams per 100 grams of H2O. At 70 degrees Celsius, we can hold 135 grams per 100 grams of H2O. So the question wanted to know how much more can we dissolve if we raise the temperature? Well, the difference will tell me how much more we can dissolve. So 135 grams, take away 105 grams, gives me 30 grams more. And there's your answer for that one. And then the next one says, how many grams of ammonium chloride will dissolve in 65 grams of water at 70? Well, I don't have a chart that gives me 65 grams, but I do have the chart that gives me 100 grams. So I'm going to look up ammonium chloride on my chart. So go back to the chart, and we're looking up ammonium chloride, so that's this guy. And we're going to look it up at 70 degrees Celsius. So go up, and it's about 60 or 61. It's just above 60, so I'm going to say 61. I'll give you guys a bit of plus or minus. If it's above a line, obviously go above. So we'll say this is 61 grams in 100 grams. So I'm going to write that down on my question or my answer here. So at, 70 degrees, you can dissolve 61 grams per 100 grams of water. But we wanted to know how many grams we can dissolve in 65 grams of water. Well, it's a proportion. If I had twice as much water, I should be able to dissolve twice as much. If I had half as much water, I should be able to dissolve half as much. So it's 61 for every 100 grams. Well, let's set up a proportion and say, how much could we dissolve in 65 grams of water? because if it's 61 and 100, then it should be a proportionate amount and 65. So all we have to do is solve for x. So again, multiply both sides by 65, and x is going to equal 39.65 grams. Basically, all I did was I solved for x. This comes up and multiplies, 61 times 65 divided by 100, there's our answer. Now, question C is just asking me for solubility. This is just a straight up reading the chart question. It asks how much can we dissolve in 100 grams of water at 50. So I'm going to go to the chart again, look up sodium chloride. So sodium chloride at the chart at 50 degrees is about here. So I'm looking at that, I'm saying that's close to 38 or 39 grams for every 100 grams, 100 grams of water. So I'll say 39 grams per 100 grams of H2O. That one's pretty straightforward. I'll do a couple more. So looking at the chart for this question, which is more soluble, NaNO3 or KCl. So we're going to look at the chart and figure out which one has always got the higher line. So NaNO3 and KCl. So NaNO3 is here, and KCl is way down here. So NaNO3 is way more soluble than KCl. So that's our answer. Next one says, how many grams of NH4Cl will dissolve in 100 grams of water at 90? So I'm going to look up NH4Cl at 90 degrees. So NH4Cl at 90 is here. And that is approximately 73. So we'll say that's 73. And we'll go back to our question here. That's all it's asking is how much we can put in 100 grams of water at 90 degrees. So I'm going to say 73 grams per 100 grams of H2O. Now it's asking for that same temperature, but on only 50 grams of water. Well, it's half as much water, so it should be half as much solute. But if the numbers aren't so nice, we just set up our ratio again. 73 grams per 100 grams of water equals x grams out of 50 grams of water. So solve for x, it's going to be half of 73. So half of 73 would be 36.5. That's what x would end up being, because we're timesing by 50 and then divided by 100. Basically, it's going in half. Now, the next one says a saturated solution in 400 grams of water at 50 is cooled to 10. So let's figure out how much difference we would get from 50 to 10, and then we can worry about this 400 grams thing later. I'll deal with that after, but let's just figure out what the different solubilities at those two temperatures are. So we're looking up KNO3 at 50 and 10. So KNO3 is here, 50 and 10. So this looks like about 24 grams. And at 50, I'm going to say, let's just say it's 84 grams. So we have 24 grams and 84 grams. Okay, so I'm going to go back to my question. So at 50, it was 84 grams per 100 grams of H2O. And at 10 degrees Celsius, I should put degrees Celsius, it's 24 grams of solute for every 100 grams of H2O. Now there's a couple ways we could do this. The longer way is we would figure out how much that would be in, each of those would be in 400 grams, and then we could find what the difference would be. Or we could just figure out what the difference is between these two and then scale it up, because that would be the difference for every 100 grams. Well, if we had 400 grams, it would just be 4 times that much. So that's what I'm going to do. It just shaves off a step. So the difference between 50 and 10, if I cooled it down from 50 to 10, the difference would be 84 grams take away 24 grams, or 60 grams for every 100 grams of H2O. The solution can't hold that much, so it can't hold more than 24. So 60 grams are going to have to settle out or precipitate out. The precipitation is the word that we use for that. So now, if it was only 100 grams, that's how much we would get. But we want this to, we don't know what would happen in 400 grams. So if it's 60 grams for every 100 grams of water, it's going to be X grams for every 400 grams of water, and it's got to be proportionate. Now, I can already tell you that because 100 to 400 is 4 times more water, so it should be 4 times more solute. But if you don't have those easy numbers, you set up this ratio and solve for x. So 60 times 400 divided by 100. Basically, we're timesing by 4 and dividing by 100. So 60 times 4 is 240 grams would settle out, or precipitate. Short form for precipitate is PPT. I just wanted to see if I had a couple more that were different. I think that kind of gives you the idea of how this needs to work. You'll have to set up these ratios to figure out if you have different volumes or amounts of water than 100 grams. If we go ahead, I just want to throw this at you a little bit because you're going to see molarity stuff. Molarity is our unit for concentration, and it's moles per liter. And basically, this allows us to start doing stoichiometry and mole conversions and all that kind of stuff. This was the last town on our mole highway. So we often talk about concentration, in other words, the amount of solute in an amount of solvent, in terms of how many moles there are in a liter, rather than grams, because everything has different molar masses. We'd rather talk in the amount of particles, or in other words, moles. So if we want to find molarity, we're looking for that. And the easy thing about this is that magical line between moles and liters literally means to divide. It's moles per liter or moles divided by liters. It's the ratio of moles to liters. So if I want to figure that out, I just have to have moles, I have to have liters, and I set them up and divide them. Well, we have grams and we have mils. So we can start by converting things to moles and converting mils to liters, and then we can find molarity. So the first thing I would do in this type of a question, I'd say, well, I have 10 grams. I want to get rid of grams, so grams on the bottom, moles on the top, of LiCl. Well, we look up the molar mass of LiCl, and lithium and chlorine added together is 42.44 grams. So 10 times 1 divided by 44.44 is 0.24 moles. Well, at this point, we have moles. We kind of had liters. I can change this to liters. 1,000 mils per liter, so this is 0.15 liters. So to find moles per liter, I just take this and divide by 0.15, liters. And then I get my answer. Moles divided by liters, the units will be moles per liter. And when I do that math, I got 1.57 moles per liter. There's how many moles you'd have in a liter of this solution. If we want to make 500 mils of 0.1 mole per liter LiCl solution, we want to figure out how many moles we would need and then how many grams we would need. So if we want to make 500 mils, or 0.5 liters, we're going to find out how many moles that would be. Well, whenever I do stoichiometry or mole conversions or any of that, I always start with a single unit, so 0.5 liters. We're trying to find moles, so I'm going to times by the ratio of liters on the bottom, moles on the top. And we have that, 0.1 moles per 1 liter. They gave us that ratio. So 0.5 times 0.1 is going to be 0.05. That's how many moles we have. And now if we take 0.05 moles, we can multiply by the molar mass, so how many grams per mole, and we've already done the grams per mole, it's 42.44 grams per 1 mole, and then we get 2.12 grams. Now I'm going to skip number 3 because it's kind of the same idea, but that gets you started anyways with mole conversions and grams and molarity. I'll stop there. I'll let you guys go through the lesson, and the next team's meeting we can go through any of the calculation stuff that you guys may have questions with. All right, have a good weekend.